we give you this thing called paths, which you will do in the GFDI, right? And I noticed the two things. Some people are very anxious to do it, right? So when the clock strikes 12, and for extra, this is why. Then there are people who haven't actually done the path for the last lecture. Fortunately, not that many, but I do know exactly who they are because, you know, in this class, nothing escapes the eyes of the evil prof. Okay, so I see every single thing is going on. I would like to encourage you to do the path thing early, fundamentally to ensure that you understand what's happening in lecture, okay, and it sinks in. After that, you have your recitation, which obviously is relatively simple problem, and then you go to DG. Then you have lecture problems as well, because I'll give you some homework to do. And then there's DG, which will be slightly more complicated. Okay, the first DG was very easy. But moving forward, I think you'll be seeing slightly more complicated problems. And again, if you just go to DG and then hope to get answers from there, you will be in trouble. Okay, the point of this class is to struggle. Okay, so the way, okay, I posted this video clip thing where this talk by this Harvard prof, right? So, as it turns out, having me give good, clear lectures is not good enough for learning. In fact, I'm supposed to confuse you. Okay, so if you feel confused, I'm doing a good job. Okay, if I'm very clear, I'm also doing a good job. Okay, so remember that it's all good, right? So the point here is that just know that it's not good enough. And after that, your missions are going to get nastier and nastier. In fact, the nastier one just opened right recently, yesterday or today, I don't remember. Yesterday, yeah. So and then it's going to get easier at the end, right? Obviously for good reasons. And then the whole point to realize here is that these guys are actually the secret to success. The lectures are important because lectures allow me to download information, okay? But the way to actually succeed and really understand what's going on is the last few things. The principle here is doing it, okay? And I want to also, how many of you have no programming background? First time you see a program or interpreter is now. Okay, very good. So the truth is that it is, okay, let's be realistic. To say that you all are, you know, kind of in, okay, let's say this, those who have programming background obviously have slightly easier life, okay, because they have seen statistics before. But to be honest, if you don't have programming background, then you probably need to put in more effort. And let me tell you what needs to be done. What you need to do is to achieve some amount of feeling for programs. You know what I mean? It's a bit like Star Wars, you know, the one whereby you just force, then you close your eyes and fire, right? Yeah, you have to achieve a certain amount of, because see, the problem is that your interpreter is not very natural. Frankly, the interpreter does some stuff that's not very natural. Okay? So, and most people who have not written programs before, they don't actually get it, you know, too soon. So those of you who have no programming background, sadly, you have to put in more effort at the first few weeks. Basically, you have to type in more code, run more code, to actually get a feel of how the interpreter works. Okay? So that's the thing. It's not the knowledge. Okay, from my experience teaching this class, it is not that the people who have learned stuff have more knowledge than you and they have advantage because they have more knowledge. Because actually sometimes it screws them over, right? Okay, they have this hard time figuring out lambdas and all the, they want to do mutation, they want to do assign this to this, so they can't do it and they're very upset. Okay, that's not the point. The advantage they have is actually having some experience with how programs run. Okay, and this is what you need to, those of you who have no background need to do to try to catch up a little bit. Okay, so some things you need to know. Just quickly recap. First of all, you must know how expressions are actually evaluated. Apply, eval. Basically, quite simple, right? You have a combination. You apply. I mean, you eval other pieces. See the first one, you apply. Okay? And then you've learned some special forms. Right, all these are the special forms that you learn. Okay, not that many. Okay, so what's a special form? It's something that doesn't do the apply, eval. Okay, so most things you do the apply. No, sorry, eval, apply. Okay, I'm a bit confused. Eval, apply. Special forms are those that you don't actually do this, right? It just means slightly different. Okay, it depends on the form. Okay, then you have learned, okay, so we have also covered some basic data abstraction primitives, which are the cons, car, and the CUDA and the list. Okay, so we have a few more, but actually there are not that many more. Okay, so we are mostly, I think as far as scheme is concerned, you are almost have learned most of the things that you need to learn already, believe it or not. Okay, so this takes stock in terms of the concepts that we've covered. So first 2 weeks we covered procedural abstraction, okay? In terms of recursion, iteration, how to convert, orders of growth, and then there's this thing called fast flip. Okay, fast flip is essentially what? Is that you basically have a kind of way to double something, to like square something, so that your index will half, right? Okay, that's the general idea. And because of that, your run time drops from linear to log. Okay, that's the general idea. And then higher procedures you've seen already. Basically, you can either put in procedures as arguments, you can have a procedure, call-out procedure as a return value, and also this idea of extracting the pattern. Okay, these are the key ideas in higher procedures. So yes, yesterday, Wednesday, we went through the beginnings of data abstraction. The question now is, how do we build up complex data types from simple data types? Essentially, the cons and the car encoder, they are like the glue to like stick simple pieces together into bigger pieces of things. Right, that's the general idea. Okay, and there are two key ideas here. First idea is this idea of data abstraction and this abstraction barriers. Right. So the whole point here is to organize your code into layers. Okay, so that the upper layer can only see one layer and cannot see the stuff below it. No, not cannot see. You can actually see, but you shouldn't use and use those things. Right. So pretend not to see. So essentially, you have a layer. You only use the next layer, and this layer will use the bottom layer. Okay. The reason why you want to do this is because if you cross the layer, then you will have this problem whereby you cannot change the implementation. Okay. These barriers separate essentially two things, like the specification or the contract from the implementation. This means that you'll be able to replace the bottom without changing any code. Right. So far, all okay? Are we all on the same page? Okay. It's quite important that you all stay with me. Okay. Any questions before we continue? Seriously. All right. If not, then we carry on for this. Okay. So the few skills that you're supposed to learn by now. First of all, you need to be able to translate algorithm to code. Algorithm means that either a math formula, or I tell you, like, the Newton's method, how this is done. You need to be able to write it into code, in scheme code. Okay. Truthfully, that's not very hard. Okay. By now, all of you should be able to do this, like, instinctively. What the hard part of the whole class is figuring out what to do. Is figuring out what is the recursion, what is the formula to be translated. The translation should be no-brainer. Okay. Then you should be able to read and understand code. Okay. Today we do some of that. Basically, you look at code, you must be able to appreciate it. Okay. So who here did literature in high school? Who here did literature? English lit. Then read Shakespeare, read poetry. Nobody did. You couldn't understand this word. Only this guy is IB guys, right? Okay, frankly, when I was young, believe it or not, I was forced to take it. I was really upset because I was a math guy, a science math guy. Wow, terrible. But as you get older, you learn to appreciate. Okay, so basically the whole point in this class is also I also want to basically teach you how to read code like poetry, and also write code like poetry. I see, wow, so pretty, very nice, elegant. All right, and scheme is really quite elegant. Okay, compared to most languages. Okay, so wishful thinking is a very important principle that you should learn very well, because it is something that you need, it's a tool you need to write your program. Okay, and finally, today we are going on to do some more about how to design and use simple data structures. Okay, so today we are going to do a kind of a demo, how a game. Okay, it's called this Game of Nim. Okay, so we'll demonstrate a few things, visual thinking, how to read code, and how to do data structures. Okay, so first of all, in this game, I'm not sure how many of you have seen it or played with it, but you should have, okay, in some way. So typically, there are two players, right? And the game consists of a pile of coins, two piles of coins, a few piles of coins, some kind of coins, okay? And then the idea here is that, each player will take turns to remove some coins from one pile. Okay, actually there's another version whereby the piles are actually sticks. Then you cancel the sticks. Okay, so the idea here is, there are some piles of coins or piles of sticks, and then you either remove coins or you cancel sticks. I mean, cancel sticks is a more natural one when you do on paper. Okay, and the one who takes the last coin or cancel the last stick will actually win the game. Okay, or you can obviously have the other one whereby the one who's last to remove the coin loses the game. I mean, it doesn't matter. There's some variants of this game are possible. Okay, so let's play the game. Okay, who wants to? I tell you what. Why don't we have our guest here? Hey, it's okay, right? Hey, go ahead, 掌聲鼓勵。Thank you very much. Okay, so, alright, so this is the game, okay? Miss Vanessa, where are you from? Well, like game show. Yes. Singapore. How come you're visiting Singapore from Singapore? So strange. Went back to study. Where are you studying? Glasgow. What do you study? Medicine. Wow, interesting. So we have a future doctor here learning from us how to write code. Very good. So you know how to play this game or not? You know how to play this game? Okay. Don't know. Let's try. Medicine supposed to be smart, right? Doctor. I also doctor, so it's okay. No. So okay. Anyway, so in this game, there are, but not that kind. So it's different kind. Okay. Now, so the point here is this: there are two piles of coins, 5 and 5. Okay. So the question here is, what do you do? Okay. So you're the player. Okay. Game show. So which pile would you want to remove coins from? Pile 1. Okay. Very good. So you type in 1. Okay. I type for you. 1. Enter. Then it asks you how many coins do you want to remove. 3. So greedy. Okay. Never mind. We try. Okay. So what happens after that? So Miss Vanessa removed 3 coins, right? And then that left 2 coins on the pile 1. And then this you're playing against the computer. The computer basically took 1 coin from pile 1, right? Okay. Okay. So how, Miss Vanessa? What do you do? The aim of the game is what? To be the last one to pick up the last coin from any pile. There are 10 coins. There were 10 coins. Now only 6. There were 10 coins. Your goal is to be the last one to pick up the last coin. Okay. Stress. Okay, then what do you want to do now, Miss Vanessa? Second pile. Okay. How many coins? 4. Okay. So so Miss Vanessa took basically, the 4 coins for the second pile. Then the poor computer forced to take 1 coin for the first pile. And I guess that leaves Miss Vanessa with only 1 coin. Oops, sorry. Which pile? Pile 2. How many coins? 1. Okay, and she wins. How? Okay, so smart doctor we have here. Thank you very much. Simple, right? Okay, so you all understand the game, huh? Alright. So let's take a look. So this is a simple game. Now, the question obviously is whether you are now able to write this game. And my point to you is to convince you that you can. Okay, let's take a look. Now, let's seen this already. Okay. Now, so what do you do to write this game? I mean, if you think about it logically, there are not that many things to do. First thing, you keep track of the game state, right? Where's the game? How many coins? Who's playing? Right? Clear? Second thing, you need to figure out what the rules are, right? The rules are quite simple. They take turns to take coins. Next thing is figure out some strategy, because there's supposedly AI, right? Okay, to play against a human. And then you need to figure out how to glue them together. These are the key ideas. Any questions? Okay, who here think you can write this game right now? Okay, so the point is, I'm just going to convince you today that you can write this game given what you know. Okay, so let's start with a simple game with 2 piles. This is what we did. Obviously, this game can be written with many piles, right? 5 piles, whatever. 2 is simple. Okay, so let's start with 2 piles. So first, you need to keep track of the game state. So what do we need to keep track of? How many coins then in each pile, right? Simple, obvious. Now, so let's do some wishful thinking for now. Let's pretend for now that we know that we have this thing called make game state. Okay, so you have a procedure called make game state. N and M are the coins in the 2 piles. Okay, somehow you call this thing, and then they will create this pile of coins and keep track of them. Okay, what else do we need? We need to do what? To figure out how many coins right in each pile, right? Okay, so it turns out that we can also call size of pile, game state, and P. P is which pile, right? The 2 piles, pile 1, pile 2. So essentially, when you call this procedure, it will return you, given a pile, it will return you the number of coins. Okay, and then obviously you want to, as David says, you must be able to remove the coins, right? Okay, so any simple. Okay, they're all ... now because we don't know, don't care. We pretend they exist. Okay, it's called wishful thinking, right? Okay, so for now, we just live with this. Okay, so let's look at the game. Okay, it turns out that this is all you need to write the game, okay? Now, it looks like a lot of code, but let's walk through this very quickly. So the first thing is this, right? This is called play with turns game state player. So essentially, you run the game, okay? and you give two things, right? Number one, what is the current state of the game? Which actually you just saw earlier, it's just how many piles, how many coins, right? Okay, but instead of keeping track of each pile individually, we have this thing called game state, which is one compound data that contains the state we want, right? And player means what? Whose turn now, right? So essentially the game starts, you have some amount of coins, somebody's turn, right? Now, then you display game state. So it's quite, makes sense, you print out the game state so the player can see what's going on, right? Simple enough, Then after that is a condition, right? First of all, you check whether game over or not, right? Okay? If game over, then sorry, I announced the winner, finish already, done, right? Okay? Now, I'm now trying to teach you how to appreciate code. It's like reading, like Shakespeare, right? Line by line, Next one, right? Equal. Now, equal player human means what? Humans playing, right? Okay. Human player what? So you play with turns. Play with turns what? You call yourself. And then what happens? You ask the human to move, and then the current game state, you pass to this thing called human move. Okay? And then you change to the computer's turn. Okay, so this guy is calling itself, right? Basically what it does is that if it's equal to human player, you call itself, okay? You ask the human to move the game state. Basically, you pass the game state to the human move, which is some procedure that takes care of the human's move, and then you call the computer's turn, right? Now, if it's not the human, it's computer, right? You do the same thing, except now you let the computer move first, and then you switch the player to the human. Quite simple, right? Anybody has any questions? No, right? So again, what I'm trying to highlight here is that the way to write this program is to logically look at the whole state flow, and then this is how you do it. Okay, now what happens when you do this? Suppose you want Mickey Mouse to play the game, what happens? It does what? Freaks out and dies, very good. So you learned something new today. Okay, so not new today, last time. Okay, so the point now is this. Obviously, okay, this is a quick example to say that sometimes you need to take care of this kind of extraneous inputs, which are kind of wrong, right? So typically, you have a whole conditions, a set of conditions. You basically often have this kind of error condition whereby you capture the stuff that kind of doesn't make sense, right? And then this is not that important, right? Okay. So now, how do you display game state? Okay. So okay. What we've done is this: we've written the program already, okay? And this is pretty much what wishful thinking, right? Because you just ask yourself how the heck to do it, you just do it, and now you pretend that everything is done for you, and then this kind of works, right? But after you wishful thinking already, you need to go and figure out the pieces. Okay, so now let's figure out the pieces. First one is display game state. This is really quite simple, right? Okay, because what you do, you just basically print the state, right? So you new line, then you print the power 1 is what, then you go and read the power 1, right? And then you print out the thing, new line, power 2, print the new line, print, and then done. Okay? This is all very straightforward, right? Okay? You all okay? Anybody has any questions? Anybody confused? Nobody's confused. He's not learning anything, right? Okay, never mind. We continue to try to confuse you again. Okay, so game over. How is game over? Okay, what's game over? Game over basically means that there are no more coins left, right? Okay, so how hard is that? Basically, go and check, right? Total, okay, what is game over? Game over means that the total size of game state is 0. What is total size? Total size basically is you take the size of power 1, size of power 2, add together, that's your total size. So game over, sorted out, right? Simple, Okay, now how to announce winner? Very simple, right? Announce winner, you just check whether who is the winner, right? If it's a winner, if it's a complement, you say you say human win. If it's not, you say bad luck next time. It's again very simple. Okay? So this is the announced winner, right? Announced winner basically see who's the winner. Okay? Yeah, good question. Why is it the other way around? Because it's the last guy this is the guy who took the last coin. Okay? So if last guy who took the last coin, I mean you just have to figure out from here, this one, right? Who basically, the last guy who took the last coin was the previous guy, and then you call the next guy. So what happened was that the next guy checked is 0, so the previous guy took the last coin, so you lost. Make sense? Okay. So that's how it works, Alright, then how do you do human move? Human move basically very simple, just ask the guy, right? Okay. Obviously right now you don't know this, but let me tell you how this is. There's this thing called prompt, okay? Okay, sorry, not prompt. There's this thing called read. So essentially, if you do this command called read, you will get this text box that you can type in stuff, press enter. Okay? So how do you do human move? Okay, what we do let star. Essentially a prompt. Okay? Which pile will you remove from? Okay, what does that mean? Prompt is this second procedure here, right? Okay, the prompt string is something to print for the player to read, and the read basically reads from the text box and returns the value of the text box, of what's read in the text box. Okay, so prompt basically will return the value of read. Okay, prompt will print the statement, return the value of read. So the value of read will become what? Becomes p, right? Okay, you see, because let p become prompt as this thing. Prompt as this thing will basically print out this statement, and then that calls to read. Read is something that you don't know, don't care. But what it does is that it gives you the box. You type in the answer, press enter. The value goes into as a return value. Okay, which then be assigned to p, right? Okay, so after that n, I do the same thing. I ask you how many coins you want to remove. Okay. Okay, and then when I prompt you, the answer read becomes n. Okay, question. Why do I do let star? So I don't need to use a V. No reason. Is there a reason? There's no reason, right? For fun, you can use let also, right? So anyway, the point here is this, right? So after you read P and read N, right? What you do? You just basically remove N coins from pile P. Okay, that's all. Right. Like this is human move, right? So essentially the human move does the following. It takes a game state. Right. It asks the user how many coins, which pile. Okay, which pile, how many coins, and then it modifies the game state and returns it. Okay? Too many coins, right? You can try and see how. Okay? So the question is, what happens if the user removes too many coins? Okay? Alright. Now the next thing you do is AI, right? Because just there's a computer move, there's a human move. Okay? And this is my wonderful AI. Okay, what does the AI do? Okay, so this is my AI lah. Okay, so AI is very smart, right? Okay, so it's really quite interesting strategy, but it's not very hard to do, right? So you look at the thing and you see, okay, you just stick one coin, right? Okay, so this is my AI, very cool. All right, questions? Okay, next. Okay, next game state. Okay, so essentially, okay, if you look back, hey, I've actually written out everything already, you know. Okay, this essentially, okay, the red one, okay, what error does? I forgot to say this. Error essentially prints an error message. Okay, it's not important. Okay, it's like a print thing. But if you look at the upper code in yellow, I've actually gone through all the pieces and finished them. Okay, I filled in all the blanks. Okay, this demonstrates to you that even now, even though you don't know a whole lot, it's actually quite sufficient to write a game. Okay, very good. Now, okay, again, so I've actually written a game, but there's only one last thing I haven't done. What is it? Which is the game state, right? The game state I told you to pretend it exists, and then how does it work? Okay, so you look at it. So game state. Now, suppose I do the following. I do make game state nm, and what I do is I multiply how many? I multiply n by 10, and add to m. I call it game state. How would you extract the m and n? One is modulo, one is remainder, right? Okay, this is what? Which is modulo, which is remainder? M is the modulo, and no, that's not true. Modulo and remainder is the same thing, right? Modulo is the quotient, right? Okay, sorry. Quotient will be n, and remainder will be m. Okay, simple, right? So what's the problem with this particular representation? Okay, you're limited to what? To 9, right? Can I change this to something bigger? How? I can multiply by a bigger number than 10, then I can keep more coins, right? Okay, so how do I remove coins? I just minus away, right? Okay, how do I minus away? Okay, basically I minus away, if power 1, I minus what? This is not, I minus this, right? Okay, very simple. Huh? Now, so the limitation is that you can only do up to 10, up to 9, sorry, not even 10. You can only have up to 9 coins per pile, right? If you guys have more, you can actually multiply by 100, 200, whatever. Not 200, 100, 1,000, whatever. Then you can move them more pieces. Okay. Yeah, correct. You can do some prime thing and some prime factorization thing. Okay, so it's possible. Now, so actually the point is this. The thing is that this one, how you can do it that way, but this one probably makes more sense, right? It's actually you'll be simpler to just take 2 pieces and glue together. Then there's no more problems, right? No more complications. So how the size of pile is what? The sum of the car included, right? Okay, sorry, size of pile is actually the car and the cooler, right? Depending on which one. Okay, this one will be the car and this one will be the cooler, right? Okay? So it's very simple, right? I mean, one other way of doing it is take 2 pieces glue together. Okay, and what you can do is you take one piece, look at the other piece, and that's it. Okay, here there's no limitation on how many coins you want to have per pile. Okay, but what's the point here? The point here is that I'm illustrating to you that there are many ways of, there are at least 2 ways. Okay, there are at least 2 ways of representing the state. Okay, and okay, how do you move coins? Basically, you figure out which part you figure out which pile it is, okay, and then you go and okay, it's a pile 1. What you do? You minus the coins from the first pile. If it's not, then you minus the coins from the second pile. Right? So it's all very straightforward. Anybody has any questions? Okay, so this is just the implementation of remove coins. Okay, so done already now. So essentially, okay, so it turns out that given what we've said so far in the last, 20 minutes, we have completely written the game. Okay, and in fact, I've given you the code inside, and I've uploaded the code for you. Okay, so this is actually sufficient, like in 20 minutes we've written the game. How cool is that? Okay, so now let's take a look at data structures. So what you need to know by now is, given a problem, okay, how to define a data structure that can help you solve the problem. So it consists of basically the representation of the state, and it also consists of some operations. Okay, and let's take a look. Okay, so there are 2 things you need to spell out. Okay, first of all, you need to specify the data structure. Basically, specification as in all the procedures they will operate on the data structure. Okay, and how they react to that. And then later on, you figure out how to implement the data structure. Okay, so the specification is this thing called a contract, right? And it spells out how to use the data structure, what does it do, okay? And then it allows other people to use it even if it's not you, okay? Implementation essentially is the inside of the data structure. So people don't have to know what to use the data structure. They don't have to know how it's actually implemented. They just have to know what it does, okay? And you have a choice of implementation. Okay, so in the Nim, right? Okay, game state. Okay, what do you have? First of all, okay, there's the game state has what? How many piles? And how many coins per pile, right? What else? What operations do you allow it to do? You got the mix state. You have got the selector, right, which is how many size of pile, and the last one is the remove. Okay. How you realize it? Basically, there are 2 ways I've shown you today. You can use the numbers, okay, use modulo and remainder. The other one, which actually is to use cons. Okay. So most times you use cons, because cons is kind of a natural thing to do in scheme. Now, so the specification, basically you typically have a few parts. First of all, you tell people roughly what the data structure does, the overview, okay, and you have to state assumptions, what you assume, okay, the contract as in what it does, and also some guarantees that and then you often also give some examples, okay. Then these are all the operations that you typically have, right? Constructors to construct the object, selectors to basically pick up parts, because normally these data structures are complicated objects, right? Because these are the smaller parts. So selectors lets you go and check each part. Okay, predicates are the testing, like true-false operators, and finally is printers to show the viewed object. Okay, so implementation, the general idea is this: there are typically many options. Okay, and in this class you learn some data structures. Okay, next class 2020 you learn a lot more data structures. Okay, And the different choices typically affect time and space considerations. We'll talk some about this in a few weeks or next few weeks. Okay, and the thing is that sometimes there are certain constraints that you will have based on the choice of representation. For example, a rational number package, right, you shouldn't have a denominator of 0, otherwise it's a problem. Okay, now in this last example for Nim, right, what? In the first representation, what is the constraint? The piles of coins cannot be more than 9, right? Okay, so these are the things that should really be stated there if it's true, okay, when you design the structure. Okay, so you implement it using, after you, okay, so I say again, the first thing to do is figure out what's the problem. Second thing to do is to decide on the representation, how you want to store the state. And after that, then, based on how you store the state, right, you need to figure out how to write code to extract state and manipulate the state. Okay, that's really the general idea. Okay, and you must ensure that your representation actually fulfills the contract. Okay, and for all places. Okay, if not, then the contract should specify which cases it doesn't actually fulfill. Okay, now so let's quickly do something. Okay, so the Nim game, basically you have this whereby this game whereby the player, the human, takes turns. Okay, now the question now is, can we modify it to allow undo? Okay, so it turns out that only the human can undo. The computer doesn't really undo. Right? Okay, so what does it do? Undo will basically remove the effect of the most recent move. Okay, and then after that it's human turn. So essentially you want to do something and then you undo it. Okay, so alright, so and it turns out that we want to let the human undo by putting in a 0. Okay, now so what are we doing here? Okay, it turns out that one of the very important things that you need to learn, or skill you need to learn, what's this Tong doing? Something in your fingers, I don't know. Look at me. Okay, so you're trying to undo something. Okay, alright, so the whole point here is that you put a 0, you undo. Okay, and so let's take a look. Okay, what this is, I was just distracted before I said something. Alright, the point is this: you need to do the following. Given a program, okay, one of the core skills is that you must be able to modify the program to do slightly new things. Okay, so what we have said earlier was that we have actually looked at how to write Nim. Okay, now suppose this requirement comes up. Now you have to undo. So how do you do this? Okay, so the key insight is this: we definitely need to figure out how to remember this thing. Right? We need to now what we need is that originally the state has only two things, right? Power 1, power 2. Okay, in order to undo, you need to remember state. Okay, more state because you need to remember what was the history of the whole game. Okay, so it turns out that before each human moves, one thing you want to do is to basically add the history, so that after it moves, you can undo the work. Okay, and when you undo, essentially what you do is that you just take the most recent history and make it the current state. Okay, that's all. So how would you do this? Okay, it turns out that there is a data structure. Okay, we'll be going through some basic data structures in this class. Okay, so this is one basic one, which is called a stack. Okay, the stack has this property called LIFO. Okay, which is last in, first out. Which means, okay, the stack can be looked at, can be seen, can be visualized in the following form. It's some kind of a little thing like this, okay, whereby you put in stuff, okay, and you can only remove stuff from the top. So the last things you put in are the first things you need to take out. Okay? Okay, so let's assume that you have a stack, okay, and the stack has these operations. Okay, I've already uploaded the code for the stack inside an IBLE. Okay, it's using some things that you don't know yet, so you pretend that you don't know what's going on, and you can actually use the stack based on this procedures for now. Okay, so you can obviously make the stack, you can push stuff into the stack. Okay, you can pop things from the stack, you can check whether the stack is empty, and you can look at what's in the stack. Okay, now let's look at operations. So suppose you create a new stack called S. Okay, so you define S to be a stack, make stack. Okay, then if you pop S, you will have nothing, because nothing to pop, it's empty. If you push S5 into S, then you push 3 into S. When you pop S, you will get which one? 3 first, right? Because you pop out the later things, and you pop out the earlier things. So you pop S, you get 3. You pop S again, you get 5. And after that, you check whether the stack is empty, and the answer is yes. Because you put in 2 rabbits, you pick out 2 rabbits, then no more rabbits left, right? Okay. So this is the code is given to you. Alright, so how would you modify it? Okay, so essentially, if you think about it, right, the place where you modify this thing is in the human move, right? Because typically, a human move, you ask the guy, okay, first power or second power. Right, so what happens now is that what you can do here is that you can add a condition whereby the power is 0. Okay, if the power is 0, you must do what? You must go and handle undo, right? Otherwise, what you do? Otherwise, the old version is just remove coins from power NP. This is the old version, right? The old version, you don't care. You give what the user gives something, you just remove it. Okay, and then but now what you do is you add three things. First, you check whether it's undo. If it's undo, you handle it. If it's not undo, you push the current game state into the game stack, before you actually do the operation. Okay. How to handle undo? Basically, you just pop the state from the game stack. Okay, sorry, I forgot to mention also. There's also an extra game stack here. You just create a game stack, okay, which is an empty stack that you can use to store the game state. Okay. Now, to handle undo, what you do is this: you just go basically pop something, the pop thing from the game stack is the last game state to be pushed into the stack. So you pop the game stack and see what's the state. If the state is old state, which nothing, then you say no more state, no more undo, right? If it's actually something inside, then you just basically go and use the old game state as the current game state, and then ask the human to make a move again. Questions? No, right? Okay. Now, so back to who asked the question about what happens if you pop too many? You, right? Okay, Palav. Well, something bad happens, right? So just as you can go and modify this, right, to do undo, you should, okay, since you are so interested in this problem, go and modify it, so that it takes care of this other problem as well. How do you basically prevent the user from doing something bad, right? Okay. So obviously this code doesn't handle that, right? All right. So summary, So what you see today is really an example of wishful thinking, right? We wish here, wish there, everywhere, and then we try this, try that, right? Okay. The general idea is take a problem, okay. At a high level, you figure out how to solve it, okay. Pretending that the things that you write automatically happen will appear somehow. After you figure out the big high level idea, you take the small parts and you implement those parts. Okay, and with that we actually managed to write a game in 20 minutes. Okay, so this is important. This happens at several levels. This can happen at the level of procedures. Okay, if you look at the game, right, I'm writing this wishful thinking thing from the level of writing all the operations, what to do, right? It also happens at the level of data structures, right? Because I pretend that this data structure exists, and then after that I went to implement the data structure. Okay, so basically the thing about data structures is there are two key things to keep in mind. First is the specification, and then you figure out how to implement it. Okay, so yeah, the abstraction barrier is the same principle. Basically, the principle here is this: I define game state and I have some operations, right? The game state was actually in one case is number. In the other case, it was a const structure, right? Okay, if I know the game state, I could have gone in and taken the game state and then did operations with it. In one case, I could have multiplied numbers, take out a modulo. In the other case, I could have done what? I could have done the cast and const and cast and CUDA, right? Okay, but if I did that, and then I wouldn't have flexibility to switch the game state between one and the other one. Okay, so that's why the abstraction barrier here is necessary to allow, first of all, to manage complexity, right? Okay, so that I don't have to know too much what's happening. And number two, it gives you flexibility to change the representation. Okay, so the key thing to understand here is that when it comes to data structures, okay, the choice of implementation, okay, you see, the thing is this, they all fulfill the same contract, right? So fundamentally, do the same thing. Okay, so what heck do you care about which is what? So the key thing has to do with performance, okay? And obviously we'll cover more of this in a few weeks, over the next few weeks. But to keep in mind that actually once you fulfill the contract, they're all the same. I mean, abstractly, all right. And the correctness of the program is guaranteed. Okay. The key difference here will be performance, which we'll talk about next week. Okay. Now, so if after this you get very stressed, let me tell you what you can do. Let's say you say Nim. Okay. Confirm win one. You lose, you can't see me. Something is wrong with you. Okay, so you feel good lah. You feel, wow, I'm so smart, right? I beat the AI. Okay, so, huh? or whatever lah. Okay, so if you feel really stressed, you can play this to feel good. If you think that you want two piles are too simple, you can rewrite nim to do more piles. Okay, and then if you think that the current computer move is no kick, then you can write a smarter version. It turns out this game is deterministic. Right, it means you can actually write a so-called unbeatable version. But that's very bad for your morale, right? You always lose, then you feel very sad. So that's why we give you this version, which is very feel good. It's called a feel good nim. Okay, but if you feel like you feel like being sadistic, masochistic, you can depends on who plays the game. You can be masochistic to play the game yourself, or you can be sadistic and make your friends play it. Right? You basically have a version that they cannot beat. Okay. The other thing that you can do is that the stack is given for you. So the point is that this typo. The stack is implemented for you. You can see how you can take the stack that we give you and do the undo. Okay. And also Palaf can go and do the checking for players taking too many coins. Okay. And you can also basically play with this and improve the nim in other wonderful ways. Okay. Draw pictures, whatever. Okay. Other than that, I think I'm done. Okay. So hopefully. Okay, what I've done this week is that I've shown you how to work with data structures. Okay, today's lecture is really an example of the what to do and how to work with this. Okay, are there any final questions? Okay, if not, then have a good weekend. I'll see you guys next Wednesday. Okay.